G'day, in this video we're going to be beginning to unpack the concept of relative velocity, and we're going to continue looking at these motion concepts but keeping it restricted to a straight line. So today we're looking at 1.1.3 specifically. We're focused on Module 1 kinematics. We're still looking at describing predicting straight line motion. That's inquiry question 1. Our content statement is all about calculating the relative velocity of two objects which are moving along the same line using vector analysis. So there are two big things that we're going to be looking at today. It's that relative velocity component as well as the vector analysis, and linking those concepts to mathematical calculations. So our learning intentions is first to be able to correctly notate velocities and accelerations which are in opposite directions, get a basic understanding of frames of reference in physics, and do some relative velocity calculations for objects in straight lines. So to begin with, polarity of a velocity or acceleration when they're in opposite directions. Now we may get a few different terms used to describe directions in a problem, but generally speaking, you might find terms like north, south, west, east, up, down, left and right, and possibly even backwards and forwards as well. Now there's a general pattern. Anything that's going north or up is positive. Anything that's south or down is considered to be a negative velocity or a negative acceleration. Anything that we see as written as east, right, or forward is given a positive velocity or acceleration. Anything that is considered west, left, or backward is generally considered a negative velocity or acceleration. This is a general convention that is pretty widely accepted for physics calculations. Next, I want to talk about frames of reference. For now, we're going to be keeping two quite simplistic frames of reference. Effectively, we're going to consider them as a point of view based on where the observer is. So for example, when we look at the clip to the right, we can actually see three frames of reference. The first one is the frame of reference of being in the stadium. So imagine that you're sitting in the stands watching these two cars. You can observe the motion of both the blue and the red car racing. From here, we can take measurements, describe things like the displacement of the vehicle, the speed of the vehicle, the velocity of the vehicle, how it accelerates, etc. But we can also take measurements from the two individual cars as well. So for example, the red car here, if you're sitting in there, from that frame of reference, you could say that the red car itself actually isn't moving because you're moving with the car. What you may observe is, say, this blue car moving forwards and overtaking the red car. You may also observe that the stadium and the road is traveling backwards from your frame of reference. On the flip side, we may say that the blue car, because it's moving faster than everything else, it's moving faster than the road, which is stationary, it's moving faster than the red car, which still has quite a large velocity, but not as big as the blue car. The blue car may experience or observe all other objects moving backwards compared to it. If you want a little bit more detail on frames of reference, there's a great video from Khan Academy, which you'll be able to find in our Microsoft Teams, which is linked in our class notebook. So when we're looking at calculating relative velocities, we're not just needing to have an understanding of frames of reference and how they work, but we're also going to have to work on our skills in adding and subtracting vectors. In particular, we're looking at collinear vectors, meaning that we have sets of vectors which are going in the same direction. So first off, I'm going to do an example where we are adding vectors together. This is something that you might do when looking at putting together multiple displacements. In our first example, we're going to have two vectors which represent two displacements going to the right. The first one is going to be a 7-meter displacement, and the other one is going to be a 6-meter displacement. So let's say, for example, we got a person, we got them to walk 7 meters to the right, and then walk 6 meters to the right again. What we could do is add those vectors together. And when we do so, we would first off ensure that we get our direction correct. Now, because there's no change in direction, both are going to the right. The final vector, the sum vector, is going to be to the right as well. We then just add the two values, the two vectors together. That makes 11 meters. What can happen when there is vectors in the opposing direction? So say this time we get them to walk 7 meters to the right, and then back 6 meters to the left. What we would do is put down a vector in the direction where the largest vector is. Here, because it's to the left, technically, the displacement is negative 6 meters traveled. You can add those two vectors up as well. So 7 plus negative 6 overall means that there is a positive displacement, meaning that as I've drawn, it's going to go to the right, and the displacement is going to be 1 meter. Now, there are also some situations where we would want to subtract our vectors. In particular, when we're looking at doing some velocity kind of vector analysis, relative velocity specifically, we may want to do some subtractions. In this example, I'm going to have two vectors. I'm going to have them both go in the same direction to begin with. The first vector is going to be 10, and the second vector is going to be 7. Now, these vectors may represent two objects. I'm going to call them object A and object B. And let's just say that our vector is representing velocity in meters per second. Now, if object A and B start in the same position, and then we both let them go at their respective velocities, what we should expect is that over time, A should be overtaking B because A is moving at a bigger velocity. But the question might become something along the lines of, how much faster is A going than B? Or how much slower is B going than A? Now, depending on what frame of reference we look at and the way that we undertake our calculation, we may be able to find both of those answers. And there's some notation that you may see around that can give you a bit of an indication of what's going on. So I have first VA, or vector A, and I have VB, vector B, or velocity B. Should probably capitalize this as well for consistency. And we can actually calculate two vectors from this. We can calculate VBA, and what that means is the velocity of B with respect to A. And what that means a little bit more specifically, when we say with respect to A is where the observation is happening. It is our frame of reference. And B is being observed. In other words, we're pretending that we're at object A and we're watching B move. So we'd be trying to figure out, is B overtaking us? Is B running behind us? And we're trying to calculate the velocity of B if we're the object A, which is moving. So in this instance, the velocity of B with respect to A is going to be equal to vector B minus vector A. So what we will do is take vector B, which is 7, and subtract vector A, which is 10. Both numbers are positive because they're going in the same direction. We find that the velocity of B with respect to A is equal to -3 meters per second. In other words, what we have is a vector which goes in the opposite direction. The value is -3 meters per second. And this vector here is V of BA. What that means is if you were at A, you were standing, you were apart, or you were on object A, or you were driving object A, or whatever the object is, if you're there and you're watching B observing from the moving object, you would see B lagging behind, that it would be moving backwards compared to you. On the flip side, we can also find VAB, which is the velocity of A with respect to B. In other words, you're on object B, or you're standing on object B, or you're driving object B, or whatever it is. You're observing from B as it's moving at 7 meters per second, and watching A next to you as it moves at 10 meters per second. So this object is moving faster, meaning that it should be pulling in front of us, meaning that the velocity that we calculate, the vector that we calculate when we do this in a second, should be positive and in the opposite direction of VBA. Now, the formula for calculating the velocity of A with respect to B is going to be VA minus VB. Now, you'll notice that there's a little bit of a pattern here where the A's and the B's in the subscript here match up with the A's in the B's in the subscript of what's being subtracted. A comes first, B comes second, and vice versa for our other equation that we have here too. So what we can do is substitute. So VA is 10, and we're going to take away 7. And in this case, we get 3 meters per second. Because the number is positive, it means that we're running in the positive direction. Remembering by convention, that means forwards or to the right in our diagram. That's 3 meters per second, which is our vector for A, or velocity of A with respect to B. Now, this is one of the first real abstract concepts which we're looking at to begin with. So if that didn't make 100% sense yet, we're going to continue to model and move in the classroom and try and give a little bit more visual to what's going on here in questions like this. But with those skills, that's going to mean that we can start tackling some practice questions, which we'll start to introduce in the next lesson. Thank you very much, everyone. In the next video, we're going to start looking at the kinematic equations. These are some of the first equations that you find in your data sheet, and will give us a lot more flexibility in being able to calculate measured values that we've already been learning about, including time, distance, displacement, speed, velocity, and acceleration. These kinematic equations begin to relate a lot of those variables together in some really useful ways. So I'll see you in the next video.